Hi there, and welcome to my video on how to find or how to take the derivative of an inverse trig function. This is kind of the last video that I have in a lesson of applications of derivative techniques for functions. And the first part of the video is showing you how the functions were derived. So I'm going to work out one of them for you, and it's going to be like what you see on the screen here. It's really based on what we know about the Pythagorean theorem and trigonometry things from previous lessons, from going back to say geometry or pre-cal. But the first three examples that we see here are just how do you actually find a rule for doing derivatives with inverse trig functions. Now, based on what we have here, we're looking at sine. So we have located, I know it looks like a y, but maybe that might be gamma or something as a Greek letter, but we'll just probably think of it as y. The opposite side of the angle, they're labeling as x, the hypotenuse is 1, and the adjacent side is what would be given from the Pythagorean theorem, the square root of 1 minus x squared. So that's essentially how we're kind of getting those things. And those are just taking the dimensions of 1 for the hypotenuse and x for the vertical segment. Those are all just, taken from the unit circle. And the third side, the hypotenuse, that's just what the Pythagorean theorem would give us based on the dimensions that we have for the hypotenuse and the vertical side. So here, this is what we know, okay? Based on what we know about inverses, if sine inverse of x, oh, nope, I'm getting that backwards. If y is equal to sine inverse of x, and you can see here we're going back to our conditional statements that never really seem to go away, then based on the properties of inverse functions where the inputs and outputs swap, then here I'm going to get sine of y to be equal to x. And this is what we want to try to differentiate. Okay, and we're coming up with that just based off of the properties of inverses from what we started with. Okay. So this is going to take a little bit of implicit differentiation because we are dealing with something with y. So the way that we're going to look at this with implicit differentiation is here taking the derivative of sine, that's going to give us cosine of y dy dx. And I'm not going to use the y prime notation that I kind of get lazy with. I'll go ahead and use the more traditional dy dx representation for the implicit differentiation. And if I take the derivative of the other side, well, that's just going to be 1. Or I can say x times d dx, but it's still going to simplify to be 1. Okay, so I have cosine y dy dx is equal to 1. And of course, just like what we've done with any other implicit differentiation, is we want to try and get dy dx by itself. So dy dx would be equal to 1 over cosine of y. Okay. Now, let's take a look at just this bit of the function. Cosine of y, what we know about cosine being the relationship of the adjacent side to the hypotenuse. In this case, we can think of cosine of y is equal to the adjacent side to the hypotenuse. Hypotenuse, I can write an h, I'm sure I can. In this case, would give me the adjacent side is the square root of 1 minus x squared over 1 in this case, which would really just simplify to be square root of 1 minus x squared. Well, if we were to try to take, now that we have that, we know what the cosine y is equal to based on what we know of the trig ratios in a right triangle. Now we're going to take this, and now we're going to swap it back in here to give us our final expression that would say, and let me, I guess, slide down a little bit here. That would say dy dx, the derivative of the inverse function, in this case, would be the same thing as saying inverse sine, or inverse sine of x would be 1 over the square root of 1 minus x squared. And that is how we're using the relationships of a triangle, Pythagorean theorem, to identify the sides, basic trig relationships to help us understand what sine, cosine, in this case cosine, would be, tangent, obviously, and how we can use some implicit differentiation to identify a nice little rule that we can use to help us do derivatives of multitudes of inverse trig functions. So what I want you guys to do, those of you that have the notes following along with this video, the next two examples, B and C, are asking you to do the same thing for cosine and tangent. So I want you guys to go ahead and pause the video at this point and work those out. And then when you hit play, you can check to see how your stuff works or looks compared to mine, okay? So go ahead and pause the video and do that. So how'd you do? Based off of the dimensions of the triangle that we have here, I know the triangle looks the same as the last one did, but you know, it's just a representation, just a model to help us identify what the sides are going to be. Again, the hypotenuse being 1, really that's kind of coming from the unit circle. But anyway, here we're going to say the opposite sides, in this case, are going to be the square root of 1 minus x squared, where the adjacent side to the angle is going to be x. And based on what we know, again, from the first example with implicit differentiation, we're going to take the derivative, or first of all, we started off by understanding the inverse relationships where the inputs and outputs change. So that's how I go from this part here to this part here, okay? Then I do my implicit differentiation for the function. I isolate dy dx and recognize that in the denominator I have a trig relationship of sine that I understand is the relationship of the opposite side of the hypotenuse. So in this case, the opposite side of the hypotenuse simplifies to just be the square root of 1 minus x squared. So plugging that back into the fraction that we had ultimately gives us the inverse, or cosine inverse of x, to be equal to negative 1 over the square root of 1 minus x squared. Okay, so there's that one for cosine, and the next one is for tangent. So again, I want you to go ahead and pause the video and see if you can identify the rule based off of the examples that we did in part A and B. Okay, and here's the last model that we're using to show where the formula came from for the inverse tangent derivative. Again, properties of inverses are going to allow us to swap the beginning. So y is equal to the inverse tan of x. So that means tangent of y must be equal to x. And so take the derivative, implicit differentiate again. Secant squared of y, or secant squared y is equal to, or times dy dx is equal to 1. So that means dy dx will be equal to 1 over secant squared of y. Again, the relationship of secant is going to be the hypotenuse to the adjacent side. So in this case, because it's squared, we square the ratio of hypotenuse to the adjacent side. And when we simplify everything, that gives us 1 plus x squared. So tan inverse of x will be equal to 1 over 1 plus x squared. And that is really just how we're getting the formulas, the rules for the three basic functions to differentiate them. Now again, those of you that are following along with your notes, here in the video on the presentation that I have, it's including some things that are not in your notes as far as giving you the domain and range of the inverse trig functions. And so if you want to copy them down and use them for your own reference. However, they're not going to be necessary for things that we are going to be doing in this presentation, or generally things I'm going to ask you to do in class about this stuff. Okay. So, oh, I feel like I missed something here. Missed something? Hold on a second, because I am definitely missing something. Hold on a second. All right, there we go. Sorry about that. A couple of pages on the presentation got swapped somehow. But this is really where, this is what we were just doing. The stuff on the left are the three inverse trig rules that we just derived, where depending on what you had for your teachers before, in any time that you did trig, you may have seen it arc sign like this, or you may have seen it as inverse, kind of like that, the way that I was doing it previously. But that's all arc sign is. It's just another way of showing the inverse. It's kind of a personal preference. Some people, I don't know, some people just like one way versus another. Like for instance, I prefer sine inverse of u as opposed to arc sine u. But anyway. Now here, if you notice, because they're using u as opposed to x, the rules no longer have the x in them. Now the expectation is that you should memorize the rules for the inverse trig stuff, particularly sine, cosine, and tangent, although you may be asked to do something with cosecant, secant, and cotangent inverses as well. Now, for the presentation that we have here, the examples that we're going to be looking at, and those of you that are going to be doing the assignment associated with this, the work that we're going to be doing is only going to be related to sine, cosine, and tangent. So if that's of any relevance to you, we're going to be looking specifically, if I could get it out, at those. Now, this goes back to just generally what I say in any kind of math class. In a geometry class, that's where you predominantly start getting introduced to a lot of different kinds of formulas. And I've always said, anytime you use a formula, it's a good idea that you write it down because it facilitates recall. So that way, if you're having to take a test where a formula chart isn't permitted, then by taking the time to practice and writing it down every time you use it, hopefully you will remember it when you really need it. Now here we have a couple of examples of inverse trig problems that we're trying to find the derivative of. And we don't need to do any kind of implicit differentiation here because we're just trying to differentiate the inverse trig stuff. So the first one really isn't going to be a huge deal. Starting with the rule, I'm going to say y is equal to, now or y prime. I'm not going to do dyd. I'm going to just say y prime for the derivative. So the rule for sine is going to be the derivative of u, or the derivative of x, whatever it worked out to be, over the square root of 1 minus u quantity squared. Now this is where we practice a little bit of u substitution. Well, what is u? Let me go ahead and get another color here. So this bit here, the stuff inside of the parentheses, that is what they're looking at as u. So we're going to think of u as being 5 to the x power. So that means u squared would be 25 x squared, and the derivative of u prime, would be just 5. And by doing that little, or that little thing there on the side that we're doing it in blue, it really kind of simplifies things as far as how we're going to plug things in, because now it's just a matter of substitution. So I would say the derivative, y prime, is going to be equal to u prime, which in this case worked out to be a 5, over the square root of 1 minus 25 x squared. And there we go. Now, of course, it's predicated on the fact that do you remember the rule for sine? Can you identify what the value of u in the problem actually is going to be? So for instance, on the next one is going to be slightly more challenging, not a ton, but if you notice, the value that we have inside of the parentheses is much more complicated than the 5x was on the last example. So let's start by identifying what's the rule for tangent. So y prime for tangent, to take the derivative, for this one is going to be the derivative of u, whatever it happens to be, over 1 plus u squared. Okay? Well, in this case, u, and black will work. U in this case is the stuff inside of the parentheses. So u is equal to the square root of 2x plus 1. So that means u squared is just going to be 2x plus 1, and u prime, the derivative of the square root of x plus 1, that would work out to be, now you have to use the chain rule to differentiate it properly, but when you do, you're going to end up with 1 over the square root of 2x plus 1. Now, again, remember, when we take the derivative of, the square root of 2x plus 1, we have to use the chain rule, take the derivative of the inside, multiplied by the derivative of the whole thing. And once we, again, kind of do the stuff on the side that I have written in black, it's really, at this point, becomes a matter of just substitution. So here, let's see what we get. U prime was 1 over the, now I'm not going to write this as a composite fraction. We just know that, the denominator of u prime, so it's going to go to the denominator of the problem. So we'll say square root of 2x plus 1 times whatever 1 plus u squared is. So 1 plus u squared in this case was the 2x plus 1. And we can see the 1's are going to combine. So that's going to give me 1 over the square root of 2x plus 1 times 2x plus 2. Oops, why am I writing a 12? 2x plus 2. Oh, get my pen. And there we go. Now the next two are going to be ones that I'm going to ask you to do independently. Okay, so here are the next two. Those of you that need to follow along, we're going to try to do a cosine example and go back to do a sine example. So again, pause the video, work it out, see what you get for both of these, and when you're done, hit play, see how your work compares to mine. Okay, there we go. Now I can. All right, guys, let's see how you did. So, for example C, not really much in the way of a challenge on example C if you have been paying attention to what we did on the last couple of examples. The u term that we're going to be looking at for the rule would be the x squared value. So u squared is x to the fourth, and the derivative of u would be 2x. So just plugging them into the rule is all we need to do. We wind up with y prime, the derivative of the inverse cosine. In this case would be negative 2x over the square root of 1 minus x to the fourth power. Now the next one on D, I imagine those of you that are working it out probably stopped where I have it boxed. Okay, so you start with the same thing that we did for the first example, where we say the derivative of inverse sine is going to be u prime, or the derivative of u, over the square root of 1 plus or 1 minus u squared. And so u term in this case is the stuff inside the parentheses of the x squared minus 1. So when we square it, we get x to the fourth minus 2x squared plus 1. And the derivative of u would just be a 2x. Now when we substitute it, make sure that you put the u squared term in parentheses because we are subtracting the expression. And we should have ended up with 2x over the square root of 2x squared minus 4. Now, if you're doing a free response question, I would completely understand stopping there. Multiple choice question, maybe you're going to have a different answer. And let me go ahead and kind of continue this one here with, let me see, what color haven't I used here? Let's go with, let's try this one. There we go. All right, something similar but not quite the same. The denominator, the stuff inside of the parenthesis underneath the radical symbol of the denominator can be simplified further. So if we say y prime, we could rewrite the denominator in this case to be the square root of x squared times 2 minus x squared. And the square root of the x squared inside of the parenthesis or underneath the radical can be taken out. Now, when we take out the x, because we don't know what it is, what value x is going to be, when we take it out, excuse me, we take it out as the absolute value of x. Square root of 2 minus x squared, okay? And so this may very well be what the answer would be on a multiple choice, as a multiple choice answer. So just FYI. Again, free response questions don't need to be simplified. Multiple choice questions typically will be. All right, so let's kind of move on. And if you feel free, go ahead and try pausing the video as you see fit to see if you can answer these two questions ahead of me, but I'm going to go ahead and work these ones out simply because of the way that they're set up. If you notice, we're kind of using transcendental functions inside of the parentheses with cosine and e to the power of x, as opposed to numbers or a more simple algebraic expression like we saw in the last examples. But the idea of how we're going to work these problems out are still going to be the same. In fact, the first one's really not going to be that much of a challenge. So the derivative rule for tangent in this case is the derivative of u over 1 plus u squared. So here I'm going to look at u in this case as being the cosine of x. So u squared would be cosine squared of x, and the derivative would be negative sine of x. And now we just plug those into the rule that we have and see what we end up with. And we're at y prime, the derivative of the inverse tangent of cosine of x. In this case is going to be u prime, so I'm going to have negative sine of x over 1 plus cosine squared of x. And there we go. And the last one, again, it may look off-putting at first, but I don't think it is really going to be that much of a headache for you guys. So again, we're using the rule for sine. So the rule for the derivative of sine inverse is going to be the derivative of u over the square root of 1 minus u squared. So we want to know what those things are. Well, the u term, let me go to a different color here, just so keep things consistent, I guess. So u in this case is going to be e to the x power. So u squared is going to be e to the 2x power, and u prime is just going to be e to the x power again. And now taking those things and substituting them into the rule for sine inverse derivative rule, y prime in this case, substituting u prime will give me e to the x power in the numerator over the square root of 1 minus, and u squared was e to the 2x power. And there we go. Now the next examples that we're going to be taking a look at here for practicing with inverse trig functions are going to kind of asks us to do things that we've done with a lot of other things with derivatives. In this case, find the equation of a line tangent to the inverse tan function that we have, and it's giving us an input and an output. Okay, so the first thing that I want to do, based on what we have, is we want to, again, kind of keeping things consistent here, the inverse tangent rule is going to be the derivative of u over 1 plus u squared. So let's see, what are those going to be? So in this case, u is going to be you can think of it as 1/2 x or x over 2, whichever you prefer. So u squared would be 1/4 x squared, or you can think of it as x squared over 4, whichever you prefer. And u prime, in this case, would just be 1/2. So plugging those things in to the rule for inverse tan, or tan inverse, we're going to get y prime is going to be equal to 1/2. So the 2 will go to the denominator. So we'll have 1 over 2 times whatever 1 plus u squared is. So 1 plus x squared over 4. Now, we're definitely going to want to simplify the denominator that we have there and see what that's going to give us. So start by distributing it to 2, and then we can get a common denominator. And I'll get 1 over 2 plus x squared over 2. So I want to get a common denominator overall for the bottom and just simplify what it's going to be. So when I simplify overall the fraction here, just multiply, essentially just multiply everything by 2 in the top and the bottom. And that's going to give me 2 over, what do we got, 4 plus x squared. So there's the rule for the derivative. That's what we've been doing, okay? That's essentially the first step. That's what we did on examples A through E a second ago. Well, now we're going to apply it, okay? So we are going to now go and evaluate it. So what is going to be the actual value of the slope when x is equal to 2? So here I'm going to say y prime of 2 will be equal to 2 over 4 plus 2 squared, and that's going to be 1 over 4 plus 4, 1 over 8, so that will simplify to be a 1/4. So this is my slope of the tangent line. Okay, so now that I know the slope of the tangent line, and they were so kind to give us the x and y values that we're supposed to be using, we can just take the x and y values that were given to us in point slope form and say the equation of the line is going to be y is equal to the slope 1/4 times x minus 2 in this case plus pi over 4. And there's the final answer of writing the equation of a tangent line to the given function. So again, process-wise, not anything new to a calculus student at this point in their instruction. Now we're just doing it with derivative of inverse tangent or inverse trig functions. Now taking a look at this next problem here, this one looks like it's going to be a little bit tricky because first of all, we don't have an inverse tangent problem, or we don't have an inverse trig problem, which in this case would be tan inverse in this case. So we have, and if we're trying to do anything where we're taking the derivative, it can't be inside of the parentheses like it is here. We have to figure out a way to take this bit. We have to get that stuff inside of the parentheses out of the parentheses. And the way that you've always done that has been to just take the inverse trig, or the inverse operation of whatever your trig value is. Okay, so let's go ahead and let me go ahead and write it out. We have tan of 4x minus y to be equal to 4x. So we take the inverse tan of both sides. So here and here, we're going to take the inverse tangent of both sides, and that will leave me 4x minus y on the left side to be equal to tan inverse of 4x. And now you can kind of start to see, how we might, apply the trig derivatives that we were using, or the inverse trig derivatives that we were using. So let's see, let's get y on one side of the equal sign by itself. So that'll give me 4x minus tan inverse of 4x to be equal to y, close my parentheses. And now take the derivative. Well, the derivative of 4x, so that's just going to be 4. Again, here, forgive me, I'm going to just write my rule here. The tangent rule is going to be u prime over 1 plus u squared, and that's going to be the derivative of the function. So kind of off to the side here, let's go ahead and do what we've been doing. So in this case, u is going to be the 4x. So u squared would be 16x squared, and u prime would be just 4. So plug those into the function, or plug those into the expression that we currently have, and that's going to give me 4 minus, and so u prime in this case is a 4, over 1 plus 16x squared, and equals the derivative. And now we can simplify the fraction on the right side, get a common denominator. And here I could stop there as again, as a free response question. I don't need to simplify it. But if I do simplify it, it would be 64x squared over 1 plus 16x squared. And there we go. So that's how we're going to take a look at that one. Now the next one here, again, the trig stuff can always be a little bit tricky, but they're telling us, they're giving us a clue in the fact that they're saying let g be the inverse function of f of x is equal to 2 cosine x. Okay. So here, this one is going to require us to put our thinking caps on a little bit and work our way through the problem. All right. So the first thing I'm going to look at here, based on what they're telling me in the problem, with the fact that we have this one here, is I want to find when f of x is equal to 1. So that's the first thing I'm going to do. Find when f of x is equal to 1. So let's set it up. F of x is equal to 2 cosine of x. And we want to know when that is going to be equal to 1. So we'll substitute the 1 here, and that'll give me 2 cosine of x on the right side. So that'll give me 1/2 is equal to cosine of x. And again, this is where we take the inverse of something and we want to know, okay, well, when is cosine of x actually going to be equal to 1/2? And according to our unit circle with the intervals that were given to us of negative pi over 2 to positive pi over 2, we're looking at just the right side of the unit circle. There's actually going to be two values that will give me a value of 1/2 for cosine. And in this case, it will be when we have pi over 3 and when we have negative pi over 3. Those are two values, input values for cosine that will give me an output value of 1/2 on the unit circle. Okay, so that's the first thing that we know. Now we have some x values that we can work with, and so let's take a look at what I need to know next. Well, now that I have that, what I'm going to look at now is based off of the fact that we know that we have some inverse functions here. They're telling us that function g is equal to the inverse of function f. So what that means is that f of pi over 3 being equal to 1 will tell me that g of 1 will be equal to pi over 3. Now we're not going to be able to use the negative pi over 3 in this case because it's I don't remember offhand. I forgot to write it down, but the negative pi over 3 is going to be outside of some limit somewhere. It's going to be outside of something that we're doing in relation to the problem. So, but now that we understand, so we've gotten some values of x's that we can use based off of the information that was given us for something being equal to 1. We've established that because of the relationships of the inverses, that f of pi over 3 being equal to 1 means that g of 1 is equal to pi over 3. So now we're being asked to find the derivative of g at 1. So this is kind of going back to inverse functions, the derivatives of inverse functions that we saw in a previous lesson. The one that immediately preceded this one, actually. So here, that's going to let me say that in this case, the derivative of the inverse, g prime of x, is going to be equal to 1 over f prime of g of x. Okay? So in this case, we're looking at it when we're looking for g prime of 1. So I'm going to say 1 over f prime of g of 1. And we know that f prime of g of 1 is going to be giving me f prime of pi over 3. Now this is really where the trickiness comes into play, because we haven't really done anything with the derivative of function f, okay? And now this is where what we're doing for this lesson really comes into play. So at this point here, it's not real clear, but this is what it's asking you to try to recognize, okay, is what is the derivative of the given function, okay? So here what we're going to be able to look at is I'm going to look at this as f prime pi over 3 to be equal to, now the derivative of the cosine function in this case is going to be negative 2 sine of x. Oh, I'm getting ahead of myself. Let's clean that up a little bit. Let's just take about the derivative itself. F prime of x, there we go, is equal to negative 2 sine of x. There we go. Now that's going to make a little bit more sense. Now we can evaluate it. So here we're going to say f prime of the pi over 3 that we're looking at in the problem still in green on the left will be negative 2 sine pi over 3. So again, hopefully we have our unit circle memorized here. Negative 2 sine of pi over 3 in this case is going to give me radical 3 over 2, which would simplify to just be negative radical 3. And that negative radical 3 is what's going to become the denominator here. So let's continue going back to my green color here. That's going to give me 1 over negative radical 3. Now again, really realistically speaking, we could probably stop there for a free response question, but if I rationalize it, if I rationalized it, that would be negative radical 3 over 3. And there we go. So this is a creative problem in the fact that it's kind of tying a lot of prior knowledge into it. Now the last example that we have in our notes here, this one's going to require a calculator to be used because the values that we're going to get, they're not going to be, you know, nice simple numbers that we have. So I would strongly encourage you to see, can you find the derivative of the given function before I start working out the problem? But if not, I am fine with you kind of following along and copying things down. Now, because of the way the function is written, there's no way to avoid doing differentiation without including or without doing implicit differentiation in this case. So I'm going to start, let me just write the function down so that way I don't have to kind of keep looking up here. So the function was x squared plus x times the tangent inverse of y being equal to y minus 1. Okay. So now let's go ahead and start doing some implicit differentiation here, or really just start taking the derivative of the expression that we have. So I'm going to get 2x here, and we're going to have to use the product rule on the next term, where it says x times tangent inverse of y. So if I take the derivative of x, that's just going to be 1, and so that's just going to leave me the tan inverse of y. And now the next part I'm going to say plus x times the derivative of tangent inverse. In this case, it is going to be our u prime over 1 plus u squared to be equal to, what do we have? Y prime, and the constant on the right is just going to become 0. So let's see. In this case, u is just going to be the y. So let's see what we got here. Let me get another color. So in this case, u, that's just y. So u squared obviously is going to be y squared. And u prime is just going to be a 1. So taking that, let's go ahead and go back and substitute some things. So I'm going to get 2x plus tan inverse of y plus, so we're going to say the x times the numerator of u prime, which is 1, so it's just going to be x in the numerator here, over 1 plus u squared, which in this case is going to be y squared. Y squared is equal to y prime. All right, now with implicit differentiation, we want to get the y prime by itself, which let's see, I'm missing something somewhere. I feel like I made a mistake. All right, let me pause the video for just a second. Let me pause the recording. Let me make sure I'm not being a complete idiot here. Give me a second. Ah, see, I found it. Something that was throwing me off. It's because I'm a big old dummy right here. I don't know why. It seems like I wrote an X in the numerator when I'm supposed to put the y prime value there. So that was just, oh, that's why I said X. Let's see. Nope. Nope, that wasn't it. Hold on. There we go. I figured it out. Here, we're going to, because we're doing implicit differentiation, I'm going to say that this is y prime. So let's keep it separate for the time being because we want to be able to isolate the y primes, the implicit differentiation. So here we're going to say y prime over 1 plus y squared is equal to y prime. There we go. And of course, because of the implicit differentiation, we want to try and get y by itself. Or y prime by itself. So let's see what we're going to do from here. We want to take the y prime term on the left side and move it to the right side. So that's going to give me 2x plus tan inverse of y to be equal to y prime minus, and here I'm going to write it as x over 1 plus y squared times y prime. We know that they're both in the numerator, but I'm doing it that way to try and make it a little easier to see that y prime is going to be a common factor on the right side of the equation. So when I factor it, so here now I have 2x plus tan inverse y to be equal to y prime times negative x over 1 plus y squared, which we will then move through, nope, golly, all right. I can factor, I know algebra. 1 minus x over, there we go, 1 plus y squared. And now we'll take that and move it over through division, giving me 2x plus tan inverse tangent inverse of y over 1 minus x over 1 plus y squared to be equal to dy dx, or y prime the way I'm writing it. Oh, ugh, man. Sorry about the mistakes on that one, but we'll get it. It happens sometimes. So now I have the expression for the derivative, and now what it was asking us to do is write the equation of a line again. So now we need to take the value that was given to us of pi over 4 and plug that into the function there. And I'm not going to go ahead and write it all down. We're going to just take pi over 4 and plug it in for the x value, and take the negative 1 and plug it in for the y value. And when you do, on my calculator, I got rounded to 3 decimal places, 1.293 to be approximately equal to dy dx. So that's the slope. So the equation of the line that we were given, remember x was given to me to be pi over 4 and y was given to me to be 1. So the final equation in simplified approximated form would be y is equal to 1.293 times x minus pi over 4 minus 1. There we go. Or if you wanted to, I did have it written down. That's most likely how I would leave my answer, but maybe, depending on what they're looking for 3 decimal places, maybe they wanted you to go ahead and expand it and simplify it through on the calculator, which would give you a 1.293x minus 2.016. I would personally be fine with either one, but I don't know, depending on who's looking at it and how it's being graded, maybe you want to go ahead and distribute it and make sure everything is in 3 decimals or something. So that is going to conclude the lesson that I have for you on properties of inverse trig functions. Hope you're able to get something from it. Main thing, making sure that you remember to memorize the primary trig derivative inverses, whatever those rules are, and make sure that you can identify what the u value is whenever you're doing it. There is going to be, as we clearly see in a couple of examples here, some implicit differentiation. But thanks for watching, guys. If you have any questions, get in touch with me. Let me know how I can help, and we'll see you in class soon. And until then, take care, be safe, and see you soon.